So a nice thing is that any technique that you've previously learned in circuit analysis can be repeated using phasor notations for voltage and current. So we don't have to relearn all our rules for electrical engineering. We can just apply them using the phasor technique, which is a really nice, powerful tool. So just as we can convert from a sinusoidal function to a phasor, we can reverse the process, first of all. That is, if we have a phasor quantity, we can then write the expression for a sinusoid. I'm not going to go into proving that. There's a good deal of complex math to support why we can go from a phasor back into the complex form. What I do just want to say is let's assume we had a voltage phasor of 100 and angle negative 26 degrees. Right. We can convert that back into a voltage, time domain voltage expression. We could write that as V of t is equal to 100 times the square root of 2 cosine of, I'm going to run out of room there, I'm just going to write phi, and phi equals omega t minus 26 degrees here. And the reason I wrote phi separate is well, one, I was running out of room, but I want to make a significant point here. You'll notice that when I went from the phasor format to the instantaneous time domain expression for the voltage, I do not have a value for the frequency. We can't know the value of angular frequency from the phasor, since the phasor information, it only carries amplitude and phase, no frequency information. So without further information, we can't fill that part of the equation in. Ohm's law, KVL, KCL, all of these rules that you've learned for circuit analysis are going to apply to voltages and currents in phasor forms. So let's write KVL in phasor form. It is the voltage phasor is equal to the current phasor times the circuit impedance. So we would say, if we were going to write this out, that V RMS at an angle of phi sub V is equal to I RMS at an angle of phi sub I times Z at whatever its angle is, theta. This is the Z angle theta, right? The RMS voltage at whatever its angle is the IRMS current, whatever its angle is, times Z at whatever its angle is, right? So what are we saying there? Well, remember that in a complex impedance, we have real and imaginary components. We've got the resistance and the reactance, so that gives us impedances that can be written in rectangular polar form, right? This just represents the combination of resistance and reactance. If I've got some sort of current waveform, the product of the magnitude of the current and the impedance have to equal the magnitude of the voltage, and the sum of the angles have to equal the phase shift of the voltage. Very important. It's internally consistent. So Ohm's law, I guess I should have written that, Ohm's law. Written in phasor form is V equals IZ. Capital V equals capital I times capital Z. More explicitly, the RMS at an angle of theta phi sub I is equal to I RMS at an angle of theta sub I times Z angle theta. You know, Ohm's law doesn't have to be in RMS quantities. If I had a peak quantity here, it just would result in a peak quantity over here, right? The relationship still holds. So a lot of times when you're using these phasor operations with Ohm's law, KVL, and KCL, we got to do a little bit of phasor math. I'm not too familiar with what you're taught in your other classes, so a brief review, you've probably already seen this. If you have, never hurts to review, right? So the first operation we want to look at is multiplication here. So we've got, this is really well represented in Ohm's law, V e to the j theta sub V. So the voltage is going to be equal to the current times the impedance phasor, or the impedance vector. We should never call that a phasor. So it's quantity 1, it's quantity 2. Voltage is equal, V equals I. Z, here we've written them in terms of their exponential form. And what we're showing here is if we multiply exponentials, we multiply their magnitudes, we add their angles, right? Multiply their magnitudes, add their exponents. In division, such as, say we were trying to calculate current based off the known voltage, we would say that the current is equal to the magnitude of the voltage divided by the magnitude of the impedance, there times e to the j, and the angle in the exponent is the angle of the numerator minus the angle of the denominator. Right? Very similarly, if we were representing phasors as angles in the angular form instead of the exponential form, we would say V at an angle theta sub V is equal to the product of the magnitudes of the current and the impedance at an angle of the sum of their angles. If we were going the other direction, say we wanted to determine the impedance vector, well, we would take the magnitude of the voltage phasor, divide that by the magnitude of the current phasor. Those would be at an angle of the numerator minus the denominator. Right? Same kind of math patterns exist in both of those. So very important, these operations. These in particular, you're going to be using these quite a bit. Right? So we'll become more handy with those as we proceed. So, like always, let's build some skill sets here by working some quick examples. The first thing that we're going to do is analysis of a series circuit. We've got a 90 ohm resistor, a 32 millihenry inductor, and a 5 microfarad capacitor. These devices are all connected in series and then connected across the terminals of an AC voltage source, given this time variant voltage function. So it's just a sine function with peak value 750, frequency 5,000 radians per second, and 30 degrees of phase shift. What we want to do is calculate the steady state current using phasor operations. So what we're going to do is first convert, or kind of mine, we're going to kind of mine this for some information. We know that V peak is 750, we know that omega is 5,000, and we know phi is 30. Should include unit 750 volts, omega is radians per second. Right. Radians per second. So what we can first do is we're going to calculate the, we're going to transform the inductor and capacitor into their equivalent reactances, recalling that reactance is frequency dependent. The reactance of the 32 millihenry inductor is going to be Z sub L is equal to, you'll remember the formula is J times angular frequency times the inductance of the device. In this case, that's J times 5,000. It was 32 millihenry, which was 32 e to the minus 3. And that's going to result in 160 ohms of reactance. You'll recall that a J preceding it indicates that we have a reactive quantity. So we want to do the same thing for the capacitor, C sub C. Hopefully by now you know that the formula for the impedance of the capacitor is 1 over J omega C. Right? So this is going to give us 1 over J, same frequency, 5,000, same angular frequency, 5,000. In this case, we were dealing with a 5 microfarad capacitor, that's 5 e to the minus 6. And that's going to result in minus J40. Again, it's a reactance, it's measured in ohms. Confirming our suspicions at this point, or what we know about engineering circuits in the frequency domain, inductances should have positive reactance, capacitors should have negative reactance. If it didn't come out that way, maybe you made a mistake, so it's a good sanity check at this point, right? The phasor transformation of the voltage is really easy. If we want to figure out what the voltage is, we're just 750 at an angle of 30 degrees. Right, so not too difficult there. So we've calculated Z sub L, we've calculated Z sub C, and we've calculated the voltage. So now we can do our math. So the problem statement said that there are series impedances. So we needed to find the total equivalent impedance, Z, E, Q, right? Well, we know that there was a resistor. We need to add the impedance of the resistor. They're in series, so they just directly sum. We've got ZL, and then we have Z sub C. So we add those up. It's remember, it was a 90 ohm resistor, and then we calculated ZL as J160, and then we're going to add the impedance of the capacitor, which was negative J40, so minus J40. So the total circuit impedance is 90 plus J120. Plus J 120 ohms. We can put that into polar form. That's going to be equal to 150 at an angle of 53.13 ohms. Okay. Well, now let's just use Ohm's law. We've got I is equal to V over Z. Right, so we take our voltage phasor, it was 750 angle 30. We divide by 150 angle 53.13. This is volts on the top. This is ohms on the bottom. What do? From our rules of math, remember we divide the numerator by the denominator and we subtract the angle of the denominator from the angle of the numerator. So 750 divided by 150 is 5, and 30 minus 53.13 is negative 23.13. So we end up getting a current of 5 amps at an angle of negative 23.13 degrees. Right. So how do I convert that back into a time domain expression for current? I of t, time domain expression for current, is the 5. Then I just put my cosine function. And then I write my omega, which was 5,000 given in the problem statement. Multiply that by time. And then I account for the phase shift, minus 23.13 degrees. And that's all in amps. Right? So one thing I do want to point out might cause you some confusion if you aren't following along all that closely, is that I calculated a value 5 here and I put it in for the peak voltage. Why did I do that? Well, remember, I calculated all my I calculated my current based off a peak. So I used Ohm's law based off peaks. So if I use the peak voltage when I'm calculating Ohm's law, guess what? The result is the peak current. If I had converted that over to do the math in RMS, then the result would have been the RMS current. So it is important to know what you're working with, whether you're in peak or whether you're in RMS, right? And keeping track of that as appropriate. So let's do a second example, right? We're going to do a second example, and we did series, so let's go ahead and do a parallel circuit. So here we have a sinusoidal current source in this case in the circuit, and it's producing a current, a time-variant current of 8 amps times the cosine of 2 million T, super high frequency. Not too realistic, but go with it, I guess. What we want to do is find the steady state expressions for the voltage across the devices in parallel, and then we want to know what the branch currents are, I1, I2, and I3 here. So we want to find the voltage here. What's the voltage? And then we want to find these three currents. Okay. So what we'll do first is we're going to determine the voltage, and how we're going to do that is, well, we know the current. If we can determine equivalent impedances of these three connected branches, we can determine the current. We can know the voltage, right, from Ohm's law. Find the Thevenin equivalent of these three. We know the current. We can determine the voltage. Once we know the voltage across each of the branches, and we will because they're in parallel, so they have the same voltage, it's a simple matter to just divide the voltage across the branch by the impedance, and that gives us the branch currents, right? So that's the approach we're going to take. Lump those into one element, find the equivalent voltage for the Thevenin equivalent model. We then know that because they're in parallel, the voltage across the terminals of all three is going to be equivalent, which allows us to determine the branch currents. So the first step, Thevenize. So we want to find the equivalent impedance of the three branches. We're going to use, in this case, we're going to use the technique of admittances that we talked about in last class. Why? Well, it's easier to add parallel elements that contain reactances if you go by admittances. It's just simpler. So what we're going to do is we're going to find the equivalent admittances of each of the components, and then we're just going to add the admittances of each branch up, and then we're going to start at the R1, and we're going to kind of move to the right. So let's do it. So let's start with R1. So we're going to call its admittance Y1. There's only one term in the first branch. It's a 10 ohm resistor, so it's 1 over 10 ohms is going to give you 0.1 mhos. Okay, Y2. There were two components, a 8 ohm inductor and a 6 ohm resistor. You can verify for yourself that turns into an 8 ohm inductor using j omega L, where omega's that value right there for a 40 microhenry inductor. So we're going to do, oh, sorry, I lost my stuff. Y1 equals 0.1 mhos. Y2 is therefore 1 over the series combination of that 6 ohm resistor and the 8 ohm inductor. I'm leaving you to determine then that's 8 ohms on your own. That's an exercise. We do that math, we get the admittance, 1 divided by 6 plus J8 is 0.06 minus J 0.08. It's an admittance, so it's measured in mhos. Now the last thing that we have to do in terms of calculation of the individual admittances is we determine Y3, the branch with the capacitor in it. I'll leave it to you to verify that equivalent capacitance, or the capacitance equivalent is a 5 ohm reactance, so that is 1 divided by, remember it's a capacitor, so it's got a negative reactance, minus J5, right? And that gives us J 0.2 mhos. Okay. Now, the nice thing about the admittances is total circuit admittance, Y equivalent, we can just sum them, Y1 plus Y2 plus Y3. We sum those up, 0.1 ohm plus 0.06 ohms minus J 0.08 ohms plus J 0.02. That's going to give us 0.16 plus J 0.12. .16 plus J 0.12. Moles, right? So we're going to turn that into a polar notation that's just 0.2 at an angle of 36.87. Still in those. They're just converting forms. So we've got a total circuit admittance of 0.2 at an angle of 36.87. Y equivalent, right? Well, I can't do anything with Ohm's law with admittances. Let's go back to impedance. Remember, Z is just 1 over Y. So 1 divided by 0.2 at an angle of 36.87. 1 in complex notation is 1 plus J 0. That's equal to 1 at an angle of 0 degrees. So if you're confused about that, just think of 1 as 1 at angle 0 degrees. Remember, we divide the two, so we're going to get Z equals 1 divided by 0.2 is 5, and 0 degrees minus 36.87 is negative 36.87. This is an impedance, so it's ohms, right? So what is that telling us? We basically have a circuit now where we can replace all of this, resistances, inductors, capacitors, with one block that's 5 at an angle negative 36.87. Right. So what we want to do now is calculate the voltage across all the parallel elements. We're just going to use Ohm's law in the phasor domain. Voltage is equal to V equals IZ. So we get the voltage. We don't know that, right? We just need to multiply I times Z. So I previously it was 8 amps at an angle of 0 degrees, and then we multiply it by 5 at an angle of negative 36.87. We've got that. Multiply that out. 8 times 5 is 40. 0 plus 36.8. 0 plus negative 36.87 is just minus 36.87. So we get a voltage of 40 at an angle of negative 36.87. Right? 40 at an angle of negative 36.87. You'll notice that I used 8 in the calculation, which means I calculated a peak value. 40 volts at an angle of negative 36.87 is the peak quantity. Right? So now what we want to do is use Ohm's law again. We're going to calculate the branch currents. So remember that the voltage across all of them is 40 volts peak at an angle of negative 36.87 degrees. And I just divide that voltage by their branch impedance to get the currents. So I1 is just going to be 40 at an angle of negative 36.87 degrees. I divide that by the branch impedance, 10 ohms. So that's going to be 4 at an angle of negative 36.87. Right. And similarly, the branch current for I2 is going to be this voltage, 40 at a negative 36.87. Oops, 36.87 divided by the impedance of the second branch was 6 plus J 8 ohms. So that branch current is going to be 4 at angle negative 90. And then the third branch current, I3, is going to be 40 angle negative 36.87 divided by the capacitance. 40 angle negative 36.87. We could write this as minus J5. Another technique that I'll just expose you to in case you ever see it is remember that J causes 90 degrees of rotation, minus J therefore causes negative 90 degrees of rotation. So we could just write this as 5 angle negative 90 degrees. That's a capacitor. And you get 8 at an angle of 53.13 degrees. So now we know the branch currents. Current flowing in the first branch is 4 amps with a phase shift of negative 36.87 degrees relative to the reference current, which was the current source in this case. I2 is 4 at an angle of negative 90, and I3 is 8 at an angle of 53.13. A good habit to get into is going to be to verify these calculations. We calculated them individually, but we know that from Kirchhoff's current law, the sum of these 3 branch currents has to equal the total source current coming from that current source, right? So, and we know how much that is. It was given to us in the problem statement. So what we're saying is this branch plus this branch has to equal the flow in, right? So let's do that calculation. What we're saying is that I total is just equal to I1 plus, there are 3 branches, right? So I3. So we have these 3 branches. So we just add the values that we just calculated. I'm going to do it in the rectangular form. It was 3.2 minus J 2.4. I'm going to add to that I2, which is minus J4. And then the third branch current was 4.8 plus J 6.4. You can verify those on your own. Sum all those up, we get 8 plus J0. Right, or 8 at an angle of 0 degrees. 8 angle 0 degrees amps is the sum of the 3 branch currents. 8 angle 0 degrees, right? So we have consistency there. If we were going to use those calculations then, if we wanted to write the steady states, remember what we would do is we would say V of t, there's only one voltage in the system. Well, there's multiple voltages in the system, but for each branch, the branch voltage or the voltage source, the voltage across the current source is given by 40 cosine of 2 million or 2e to the 6th times time. Remember, there was a phase shift between the current source and the voltage of negative 36.87. degrees. That's in volts. We can then write the branch currents. I1, that's going to be equal to 4 cosine of 2e to the 6th t minus 36.87. We'll notice that, that's degrees, that's amps. Notice that the voltage and the current in the resistive circuit are in phase, as they should be, right? There can't be any phase difference in a purely resistive circuit. The next branch had a inductor and a capacitor. No, it didn't. It had a resistor and an inductor. So we know that there's going to be some phase shift between the voltage and current based on the relative size of the impedance and resistance. In this case, it is 4 cosine, so same amplitude, 2e to the 6th t. What was the phase shift here? It was minus 90 degrees. Amps. So 90 degree out of phase with the source current. And then finally I3 of t we write as 8 cosine of 2e to the 6th t. This one's interesting, plus 53.13. Why is that interesting? It should be 90 degrees, yeah it is, it's 90 degrees out of phase with the voltage waveform, right? That's a capacitor. We know that the voltage and current in a purely capacitive circuit, remember Eli the Iceman, in a capacitive circuit, voltage lags current by 90 degrees. If I take 53.13, subtract 90, I get minus 36.87. So, because this is a purely, remember the third branch was purely capacitive.